Good day. Now, we will be answering problems from Chapter 27, Magnetic Field and Magnetic Forces. So we will answer problem numbers 27.52, 27.54, and 27.64. So the first problem is problem 27.52. A particle with charge 7.26 times 10 to the negative 8 coulomb is moving in a region where there is a uniform magnetic field of 0.65 Tesla in the x direction, positive x direction. At a particular instant, the velocity of the particle has components Vx, Vy, and Vz. Vx is negative 1.68 times 10 to the 4 meter per second. Vy is negative 3.11 times 10 to the 4 meter per second. And Vz is 5.85 times 10 to the 4 meter per second. Then the question is, what are the components of the force on the particle at this time? So to solve this problem, we will apply the formula for the magnetic force, which is magnetic force is equal to charge multiplied by the velocity cross the magnetic field B. And let's write the V cross B in its determinant form so that we can easily write the equations for the components of the forces. Then in the situation, our magnetic field acts on the positive x direction. Therefore, Bx is equal to 0.650 Tesla. There are no y component of the magnetic field and there are no z component of the magnetic field. Now, let's solve for the force along x. So using this determinant form, so the force along x is equal to the charge Vy Bz minus Vz By. Since our Bz is 0, therefore this is 0. And since our By is also 0, this is also 0, giving us the 0 force along the x component. Next, for y component, so using this, Vz times Bx minus Vx times Bz. So multiply it by the charge Q. We will cancel this term because the magnetic field along Z is 0, leaving us with this term. So substituting the values, so this is the charge of the particle, this is the velocity along Z, and this is the magnetic field along X. Solving this, we will get 2.76 times 10 to the negative 3 Newton. So that is the force along Y. Then lastly, let's solve for the force along Z. So to solve that, let's multiply the charge by Vx times By minus Vy times Bx. Since our By is 0, so we will cancel this term and leaving us with this term, which will be multiplied by the charge. Inputting the values, we have negative, this is the charge, and this is the velocity along Y, and the magnetic field along X. Solving this, we will get 1.47 times 10 to the negative 3 Newton. So this is the force along Z. This is the force along X, the force along Y, and the force along Z. So those are the components of the force on the particle at that time. Next problem, problem 27.54. Magnetic moment of the hydrogen atom. In the Bohr model of the hydrogen atom, just see section 39.3 of the book. In the lowest energy state, the electron orbits the proton at a speed of 2.2 times 10 to the 6 meter per second. In the circular orbit of radius 5.3 times 10 to the negative 11 meters. What is the orbital period of the electron? And if the orbiting electron is considered to be a current loop, what is the current I? And what is the magnetic moment of the atom due to the motion of the electron? So to solve this problem, we will use the following. So the circumference of a circle is 2 pi r. The magnitude of the electron's charge is this. And then the area of the orbit or the circle is pi r squared. Now let's solve for the orbital period t of the electron. So in solving that, we have the distance traveled by the electrons, which is the circumference of the circle, which is 2 pi r, divided it by the velocity of the electron, and we will get the time it takes for the electron to revolve around the proton. Substituting the values, we have 2 pi, the radius, over the velocity of the electron. This will give us 1.5 times 10 to the negative 16 seconds. Now, finding the current I if the electron is considered a current loop, we will use this formula. So, charge divided by the time. So, this time is the orbital period. Substituting the value, the charge is this, and the time it takes the atom to revolve is this, giving us the current of 1.1 times 10 to the negative 3 ampere, or 1.1 milliampere. Then lastly, for part C, what is the magnetic moment of the atom due to the motion of the electron? So calculating the magnetic moment of the atom due to the motion of the electron, we will use the magnetic moment formula. So mu is equal to IA, current multiplied by the area. So the area of the orbit is pi r squared. Inputting the values, this is our current, pi times the radius squared, giving us 9.7 times 10 to the negative 24 ampere meter squared. Okay, last problem, problem 27.64. A plastic circular loop has a radius r. So this is it. And a positive charge q is distributed uniformly around the circumference of the loop. The loop is then rotated around its central axis. So this is the central axis perpendicular to the plane of the loop with an angular speed of omega. If the loop is in the region where there is a uniform magnetic field B directed parallel to the plane of the loop, calculate the magnitude of the magnetic torque on the loop. So to solve this problem, we know that turning the charge loop creates a current I, and the external magnetic field B exerts a torque tau on that current I. The formula for magnetic torque is tau is equal to mu, which is our magnetic moment, multiplied by the magnetic field B sine phi. In the problem, it reads the loop is then rotated around its central axis perpendicular to the plane of the loop, giving us the angle of 90 degrees. The formula for magnetic moment is current times the area. Substituting the value of mu to this mu, we will have torque is equal to the product of current, area, and magnetic field. Now, solving for the current, or finding the current I, we know the formula for current is I is equal to Q, or the charge, over the period. And given that the period is the inverse of the frequency, or 1 over F, substituting T with this T, or the period, we will have I is equal to Q over 1 over F. Simplifying this, we will have QF. And we know that the angular velocity is equal to 2 pi F. Rearranging this to get F and substituting it to this F, we will have Q quantity omega over 2 pi. And simplifying this, we will have charge times the angular velocity over 2 pi. Now going back to this equation, we will substitute this value of I to this I. So we will have magnetic torque is equal to, this is the current, Q omega over 2 pi times the area, which is pi r squared, times the magnetic field B. Simplifying this, we will cancel pi and this pi, leaving us with 1 half Q omega r squared D. So this is the magnetic torque.